Hello, dear learners. My name is Professor Janku. Once more, welcome to our session. You're advised to please like, share, and comment this video. You're also welcome to subscribe to this YouTube channel for more mathematical content. At this point, the theme of our discussion is how to apply trigonometry to solve problems in 3D. Welcome to this educational journey through practical trigonometric applications. So let's discover how these powerful mathematical tools can be used to solve real-world problems. The learning objectives of this session is to help you review a few trigonometric principles, and you're going to see how to apply these trigonometric problems to solve, these trigonometric principles to solve problems in 3D, 3 dimension. You're advised to recall a few trigonometric techniques or principles or rules. Among these trigonometric rules, we have the area rule, we have the cosine rule, we have the sine rule. With regards to the statement of this rule and when to apply this rule, you're advised to watch our previous video. You're also required to recall a few trigonometric ratios like the sine, cosine, tangent ratio with regards to right angle triangle. You're also encouraged to recall a few trigonometric identities. With regards to trigonometric identities, there are a lot of videos that I've uploaded on this session, so you're also advised to watch those videos. When you're given a question in three-dimensional space, what you have to do is to first check what are the information, identify what measurements you have at hand, and then apply the appropriate rule based on your available information. You can apply the sine, the cosine, the area rule, or any other trigonometric principles to solve this. So always identify your known sides, your known angles before going ahead to solve the problem. Let's check out this basic approach with regards to how to apply trigonometry principles to solve problems in three-dimensional space. We are going to use this example to show you what to do when you encounter such a problem. So here we have our sketch. In this sketch, we have A, B, and ED, which are vertical towers. And from a point C, we have B and D on the same horizontal plane. We have the angle of elevation to A, which is theta, the angle of elevation to E, which is 2 theta. And we also have in triangle EBC, we have the angle given by 90 degrees plus theta. In triangle BEC, we have the angle given by theta, and the length of side BC is given by X. The first question, we have to determine in terms of theta and X, the side BA. How do we go about it? We first have to find out what are the sides which are known. Remember, BA is this tower here. And in this tower, we want to check what triangle corresponds to this. So we have the triangle ABC, which is a right angle triangle. Why do we choose this? Because in triangle ABC, we have our right angle triangle, we have the angle given here, theta, and we have the side here given here, x. So we want to find now a ratio which combines the angle AB, the side AB and the side BC, because we have BC, which is known given as x, and we have the angle theta. So what we have to use now here is to find a ratio which associates the opposite and the adjacent. The opposite is what we are looking for, and the adjacent is given as x. So the ratio which best corresponds to this is tan of theta, which is equals to opposite over adjacent. And the opposite in this case is actually our BA that is known, and that we're looking for, and the adjacent is x. Therefore, x is equals to, or precisely BA is equals to, let's have our BA that we're looking for. BA is equals to x times tan of theta. And that is what we have in regards to BA in terms of x and theta. This is part A of the question. Part B of the question, we want to determine the length of side EC, still in terms of theta and x. In an attempt to find this, we go to our diagram and see where is EC in this diagram. We have EC here. What triangle can we consider in this case? We can consider triangle EBC. Why do we choose triangle BEC? Triangle EBC, simply because we are given our angle B here in triangle EBC as 90 degrees plus theta. We are given angle BE or angle E in triangle BEC as theta. So what do? We now have to make use of the sine rule. Why our choice of the sine rule? Because we have two angles given, one side given, and the other side is what we are looking for. Therefore, let's move ahead and use the sine rule here. According to the sine rule, check our previous video if you don't remember the sine rule. We're going to have EC divided by the sine of the angle B in triangle EBC equals to x over sine of what? Angle E in triangle BEC. So our side EC is equal to x times sine of, remember, we're given in the statement of the problem that the angle B in triangle EBC is given by 90 degrees plus theta. And our angle E in triangle BEC is given by theta. So we cross multiply, right? So we're going to have this, multiply this to the side. This is actually what we're going to obtain. So in terms of x and theta, the side EC is given by x times sine 90 degrees plus theta divided by sine of theta. Let's move on to the next question. The next question, remember, is or demands us to show that ED is equal to 2x times cosine squared of theta. How do we obtain that? We go back to our sketch and determine where is ED. So we have ED here. We can easily see that we can have this angle. We can consider triangle EDC, which is a right angle triangle. What can we use here? We have 2 theta for this angle C here. We can use our trigonometric ratios as well in this case because we're dealing with the right angle triangle here. Let's move on to obtain or to show that ED is given by that expression. We're going to have, this is the next proof, sine theta, our trigonometric ratio, is given by what? Opposite over hypotenuse, which gives us ED divided by EC. And ED is what we are looking for. So this implies ED is equals to the side EC times sine 2 theta. We remember from our previous calculation that EC is given by x times sine of 90 degrees plus theta divided by sine theta. Don't forget to multiply by sine of 2 theta. Remember our co-ratio identity. This is equals to x times cosine of 90 of theta, cosine of theta times sine 2 theta divided by sine theta. Remember our trigonometric identity for sine 2 theta, which is equals to x times cosine of theta times 2 sine theta cos theta divided by sine theta. This cancels, and the answer is 2x times cosine squared of theta. And this is what we have to prove. We are done with this part. What is the next question? We are required to determine the value of the sine ED divided by BA if theta is equal to 12 degrees. From our previous made calculation, we did obtain the value of ED and BA. We just need to substitute it into this expression. So we have ED over BA. Our ED from our previous calculation is 2x times cosine squared of theta divided by BA. This is our BA, x times tan of theta. This x cancels with this x. We're going to have 2 times cosine squared. We're told that theta is equal to 12 degrees, so we're going to have 12 degrees here divided by tan of 12 degrees. If you put it into your calculator, you are going to obtain 9. So this is how we can use our various trigonometric principles. Always remember, when you're given a problem, observe. If you're not given a sketch and see the known sides, the known angles, and see what trigonometric principles apply. It can be area rule, it can be the sine rule, it can be the cosine rule. You all know at this point when to use these rules. It can be the trigonometric ratios when you're given a right angle triangle. So always know all those principles by your fingertips in such a way that when you're given a problem, be it in 2-dimensional space or in 3-dimensional space, you should be able to know how to apply this. As a summary, we have covered the trigonometry principles for triangle calculations. We've shown you how to use it to solve 3D problems, and you are advised to practice more examples. Practice with more examples to build your confidence in applying these concepts. Once more, thank you for joining. Please like, comment, share, and subscribe to this YouTube channel. Thank you. See you in the next video. Bye.